more about our quadratic function. So as we saw, the basic shape is the parabola, and the most basic parabola, y equals x squared. Combined with the linear function, basically all polynomials are built from these two functions. That's why they are so important in our work. So every polynomial can be factorised down as a combination of linear and quadratic factors. So the basic quadratic is x squared, and just like we saw with the basic line y equals x, you can create all quadratics by transformations, using a translation, a rotation, a reflection, or combining all those things together. How do you recognise it? Well, now one of the pronumerals' highest power will be 2. And usually we see it as y equals an x squared, but it doesn't have to be, of course. If you've got two pronumerals, one of them squared, one of them's not, you've probably got yourself a parabola. Now, some ideas. Remember this method, completing the square. This can be useful. If I can complete the square on the equation of the quadratic, it's a different way of being able to find the vertex very quickly. So I'd end up with something like this. I'd have the completed square, x minus h squared. It might not be monic, so there might be a constant out the front. And we might have another constant as well because of the technique of completing the square. The vertex then ends up being hk. So the equation is telling us something about the shift of the curve. A is telling us about the concavity, of course. Same example as yesterday. So x squared plus ax plus 12. How would I have done it using this idea? If I complete the square, well, I know the coefficient of x is 8. When I complete the square, it will be factorised to get half of that coefficient. So I know it's going to be x plus 4 squared. But when I expand that out, I don't get 12, I get 16. So I have to subtract 4 to balance it out. So I can now read off this straight away, that the vertex is minus 4 minus 4. Right? Because it's x minus the x value of the vertex, and then the constant number gives me the y value of the vertex. So there's minus 4 minus 4. X-intercepts. Well, now that I've completed the square, I can move the 4 across and solve that. So x plus 4 is plus or minus 2. X becomes either negative 6 or negative 2. This question we looked at, write down a quadratic with the roots 2 and 8 and vertex 5, 3. Well, I could now do it this way, because if the vertex is 5, 3, I know it will end up in the form some constant times x minus 5 squared, so x minus the x value of the vertex, and then plus the y value of the vertex, so plus 3. Substitute in something. Now, the other information, I've actually got 2 bits I could use. I've got the roots of 2 and 8. Doesn't really matter which one I use. So I'll substitute in 2 naught, and we can work out what k is. And there's that negative 1/3 that we saw yesterday with this example. And so there's the equation in the completing the square form. I could, of course, expand the whole thing out, and I would end up with the same equation. So that's the completing the square idea. There's another way we could do it as well, using this thing we call the discriminant. And the discriminant is b squared minus 4ac, that bit under the square root sign in the quadratic formula. So that can give us a lot of information. It turns out the vertex, well, we know the x value is minus b on 2a. The y value of the vertex will always be minus the discriminant on 4a. Now, knowing that is quite useful for questions where they say find the maximum value or the minimum value. So I don't actually need to know the x value of the vertex, I just want the y value. So rather than working all that out, I can just go straight into, or minus the discriminant on 4a, and that will give me the y value, the maximum or the minimum value straight away. Finding the zeros, well, there's the quadratic formula. It becomes negative b plus or minus the square root of the discriminant, because the discriminant is that b squared minus 4ac. Here's some interesting things about the discriminant. If it is a negative number, that tells me straight away there's no x-intercepts, because think about what that means. You're finding the square root of a negative number. Well, we can't find square roots of negative numbers, so there must be no solutions, no x-intercepts. If it's equal to 0, that means we've got something that just touches the x-axis, because there's only one solution. And if it's greater than 0, then all right, we know there's going to be 2 x-intercepts, because we'd end up with plus or minus the square root of that number. Okay, back to that same example. So y equals x squared plus 8x plus 12. I'll work out the discriminant. It's 16 for this one, b squared minus 4ac. So the vertex will be minus b on 2a, so minus 8 on 2, minus the discriminant on 4a, so minus 16 on 4, which is minus 4 minus 4. Okay, so a bit more about this thing we call the discriminant. It tells us also whether the roots are going to be rational or irrational. Discriminant is greater than 0. That tells me I've got two solutions, two x-intercepts. Or the way we say it, they have two different real roots. There are going to be two different solutions. It will cut the x-axis twice. If it's equal to 0, it still has two roots. It's just that they're the same. It's what we call a double root. So there are two equal real roots, but that means it touches the x-axis just once. And if it's less than 0, it still has two roots. Problem is, they're not real. So for the sake of the extension 1 course, we just can simply say, well, there's no real ones. There's no real roots. If you end up doing extension 2, this will change to be, oh no, there are two complex roots or two imaginary roots. But it will never touch the x-axis. If it turns out the discriminant is a perfect square. Well, if it's a perfect square, that means we can find the square root of it. So we must have ended up with rational roots, because we don't have a square root of something. So let's describe the roots of this particular quadratic. We'll find the discriminant. It turns out to be 60. That's greater than 0. So all the different things I can now say about the roots. There's going to be two of them. Well, there's always two of them. They're going to be different. They're going to be real. And they're going to be irrational, because we don't know what the square root of 60 is. So we can get all that information from that one number. But now they're saying, look at this one. There's no solutions, there's no real roots. So what could k be? What could it be? I know that unreal roots occur when the discriminant is less than 0. And by the way, when you're doing your solution, you write that sort of line down. Remember, you're presenting your solution for someone else. It's not for you. So if you just jump straight into the inequality, person reading your solution is going, what are you doing this for? What's the point of this? So you're explaining what you're doing. You say, well, hang on, I want to solve this question. I know that unreal roots occur when the discriminant is less than 0. So there's my reasoning, there's my justification for this equation. In other words, minus 4 squared minus 4 times 2k must be less than 0. K is greater than 2. There's our values of k. Alright, so 3e and 3f we shall add to our list.